So before we start, we're going to have a few words from the director of the MSR Redmond Lab, Rico Malvar.
Thank you, Yuval. I'm actually surprised to see all of you here. This is a much bigger event than I thought it would be, but I'm gladly surprised to see that this is the case. I remember when we had the sad event about Oded's passing. We all felt that very much. And very soon after, when we had an event here in MSR, then about celebrating his life, and Yuval mentioned we should also have an event to bring the community together. And from day one, I felt that was a great idea, and we supported the idea very much. But we carefully kept our expectations low. So I'm very pleased to see all of you here. Oded was a great member of our community here. Unlike most of you, I didn't have the pleasure to interact with him that much, just a few conversations here and there. But since you've all mentioned stories, I'll share one. We'll just add a little bit to what you already know much about him. I was always impressed, of course, like most of you who know him now, how smart he is, how quickly he would pick up any particular conversation and add to it. And a couple of things that were interesting in particular that show that. It's when we have these group reviews here at Microsoft. So every year the research groups have to present a little bit formally what they've been doing and all of that. And I'm there, and so I watched the presentation. And Jennifer at the time was the manager of the group, and they were presenting very nice work. And
And Christian.
I'm sorry, Jennifer and Christian.
Only mention the loud one.
Right. And now, you guys are now driving the whole lab, which is wonderful. It shows that our investment in these areas and related areas keeps growing. And Oded had an influence on that for sure. But the interesting thing on that particular presentation is that he was actually not presenting, and one of the postdocs was presenting about their work. And I remember asking a couple of questions about the work. And for some reason, I think the person, I'm not going to mention the name and all that, misunderstood the question, and it thought it was a big criticism or something. And you could sense in the person how uneasy he was feeling. And Oded kind of got the whole thing, got what I wanted to know about the question, and then very calmly interceded and made some comments about that. And then I say, oh, okay, that makes sense. And then he said a few words to the person, not really to me, saying, oh, this was great because you were able to show this, and that, and at the same time answered my question. So basically in one statement, he cleared my concerns, he cleared that person's concern, and everything was back alive, and everybody was super happy. Then I saw, wow, this is great work. And the person was like, whew, finally, this is out of the way. And that's just one example of how he was always on top, even if he was there in the little corner, and you might even think he was not paying attention. On the contrary, he was completely on top and rescued that person. And I think that is one aspect that shows how good I believe he was, and you've all mentioned that to me many times, in terms of his connections to people, collaboration, and that's just one more example of that. Anyways, I just wanted to share one little story with you. That's one I have. Once again, thanks to Yuval. Congratulations to putting this event together. Thanks to all of you for coming. This is a great event, and I hope you have a very good second day. All right.
Thank you.
So now it's my pleasure to announce the talk by Omer Angel from UBC, Limits on Limits of Planar Maps.
Thank you. And it's a pleasure to be here. It's been a very nice visit so far. Well, let me just get right to it. So this is a planar map, and since this is going to be an introductory talk, so even though there are some big experts on this in the room, I'll give almost all the definitions. So So essentially, it's just a planar graph, and it's embedded in the plane, but we don't really care about how it's embedded. So if you distort the plane with the embedded graph, we consider it as the same planar map. So we only are interested in the combinatorics of what is connected to what and in the order in which things are connected, but not in the specific embedding. Okay, so that's one thing. So now we are interested in, to start with, in two different types. So there's triangulations or maps in the sphere, and then there are maps in a disk. And one more comment that's in here. So frequently we are interested not in maps just in the graphs, but also in rooted maps. So in a rooted map, we just have a marked edge, which just which we think of as the root. This is mostly for technical reasons of eliminating symmetries, but still it's a convenient assumption. So this is an example of a particular map. Here it's a triangulation in the sense that all faces are triangles. But as you can imagine, there are many other variations. So that triangulations where all faces are triangles, quadrangulations have four-sided faces. You can consider k-regular faces where the graph is, where every vertex has degree k, or you consider several other restrictions. You could allow mixtures of those. You can have connectivity constraints. You might want it to be three-connected. So you can consider variations where things are also colored, and the colors have some interactions, but that's getting a bit far. And the interesting thing is, just as random walks under mild conditions behave to the same universality class, it's believed that all of these structures belong to the same universality class, meaning that if you take such a random class, such a random structure, you take and you take a very large one, it looks more or less the same, at least in the large scale, as if you took any other distribution. There's one more way of thinking about this. So these pictures are shamelessly stolen from Duplantier's talk a couple of days ago, and some of the other pictures are also taken from other talks, so they might look familiar to some of you. So there's another way of thinking about it, which is in terms of a random surface, and this is part of the reason people were interested in this. So what you see here is, you can think of it either as a triangulation or quadrangulation. Let's think of it as a triangulation for a moment. And you can think of this as having some triangles which are just glued together. So there's the analogy between the random walk, which is sort of as the drunkard's walk. So there's a story that these surfaces are like the drunken quilt maker. So he has a lot of pieces, so there are triangles or squares, and he just takes one and glues it to the previous one or saws it. And each time he takes another piece and saws it, and eventually you get some surface, but instead of being flat and comfortable, you get something that looks like this. So these are some of the interesting questions that we have about this. So we have this random structure, and we want to know what does it look like. You take one with 1 million vertices. What does it look like? Is it similar to the Euclidean lattice in some sense? Is it hyperbolic? So that's one question. Then there are questions about the scaling limits. So you have this. Structure. You can try to rescale it. Try to see if you get some limiting object like Brownian motion. And then there are some interesting questions about conformal properties. So you have a random surface. If you think of it not just as a graph, but as I mentioned, as triangles or squares that are sewn together, then you can think of it as a surface, and you can try to ask questions about its conformal properties. There are, of course, many other questions and I'm not going to talk about all of this. So this is a simulation of a large triangulation done by Gilles Schaeffer. It doesn't look planar because it's embedded not in the plane, but it's embedded in 3 dimensions. So you can think of it as a sort of a surface. And you can see various phenomena. It certainly doesn't look very regular like a sphere. You see that you have these areas where you have clumps of a lot of points clumped together. So this is another picture again from Duplantier's talk of the same object, so not exactly the same, but the same structure. So you have a triangulation, and it's embedded in 3 dimensions as a surface. So Okay, so it's fairly clear that it doesn't quite look nice and smooth, but exactly how rough it is a more interesting question.
Could you clarify, is embeddability in free space a constraint or not?
So it's a two-dimensional surface. Topologically, it's a sphere.
Right.
So,
but not all random spheres presumably are embeddable in free space.
well, so this is a discrete one. It's a finite. This is a finite thing, so there's no problem. So.
Oh, but I'm wondering, the lengths are not all.
So it's not isometric embedding.
It's not an isometric embedding.
I see. Well, that's what I'm wondering. So how's it drawn?
Usually the way to do these things, you try to find some energy minimization. So you try to keep the lengths similar, but you can. So that's the way both of these pictures, I believe, were generated. Okay, so a very brief overview of the history of this topic. So there are several directions from which people came to this. So physically, people thought of this. It's called two-dimensional quantum gravity in physics. And again, the idea, as written there, is to take some average of various quantities over surfaces instead of over paths, which is done with Feynman integrals. And particularly interesting aspect is the KPZ formula. So this is a relation between critical exponents of critical models in Euclidean lattices in 2 dimensions and the corresponding models on these random graphs. So just as you can do percolation, you can think of self-avoiding walk or Ising model on the 2-dimensional lattice. You can also perform these models on these random graphs. You can compute the exponents, and the nice thing is that in these random graphs, in many cases, the exponents are much easier to compute. And the KPZ relation allows us to go from the exponents in this quantum gravity setting to the exponents in the lattice. So there are some works by Bertrand Duplantier and others relating that were used to compute the exponents in Euclidean lattices along these lines. So I should say there are steps in this approach that are not completely rigorous. So there's some progress, but okay. So that's about the physics.
Omer, is this an old slide before the Duplantier-Sheffield work?
No, it's a very new slide, and the Duplantier-Sheffield work is certainly a big piece of making these things more rigorous. So some parts of concerning the relations to the scaling limits are still open, and I'll say a word about this later. Okay, so that's the physics motivation. Mathematically, so it's a very natural object to take a random planar graph. There's the four-color theorem, which was a big motivation for studying them. And Tate has a program in the 60s which he didn't push through to prove the four-color theorem, but part of it involved enumerating planar maps. He developed some techniques for enumeration. So he came up with various formulas, including this one for the number of triangulations of a polygon with a given number of internal vertices. So why do we want to talk about polygons? So you'll note that here I just have an external face which is not a triangle. So this is a triangulation, but we have one external face which has a different size. And frequently these things turn out to be useful. In fact, in order to even write down the recursions that he developed, you need them. So very roughly, the idea is that if you have some planar structure, so you pick an edge, maybe the root edge or one next to the root edge, and you ask what happens if you delete the root edge. So there are two possibilities. One possibility is that you have sort of a bridge, and then you get two disconnected maps. The other possibility is that you delete this, so you have some face here which is no longer part of it, and you get a smaller map. So this allows one to write recursions for the number of such objects, and then there are some non-trivial techniques developed to solve this. So the precise formula is not so important. What's more important is the asymptotics. Yes?
Does it also give a procedure for simulating a random one?
Yes. You can use these recursions to simulate. essentially, because you have once you have the enumeration, it's possible to simulate. Okay, so the more important thing is the asymptotics, and what you'll note, so the number of triangulations of a polygon with boundary size m and n internal vertices. So you have some constant depending on the boundary, and you have an exponential term, in this case 256 over 27 to the n. And then you have n to the minus 5 halves. And the interesting thing is that, so this constant 256 over 27 is not so interesting. So this is dependent on the model where you take triangulations, quadrangulations, and so on. And the exponents of 5 halves is the universal one. So in every class of maps that were enumerated, you always get the same type of asymptotics, the same exponent. And this exponent can be seen from some of the arguments as a bigger effect on the structure of these objects than the exponential term. Okay, so this is about enumeration, and I have to say, so more recently there were newer techniques developed for enumeration, bijective techniques. So this was pushed forward quite a lot by Gilles Schaeffer and his co-authors. So the idea is that you have a bijection between the set of planar maps of a given class, say quadrangulations. So the nicest constructions in the case of quadrangulations are the duals, which are for regular maps. So those also have the simplest formula. So you have a bijection between those and a tree, a plane tree. So that's a tree where the children of each vertex are ordered. And there is also some additional structure. And very roughly, you can think of this additional structure as telling you how to take this tree and glue together different parts of the tree to get a surface. So I'm not going to say much about this, except that these bijections have turned out to be extremely useful. Okay, so I'm going to talk about limits of planar maps. So there are two types of limits that we can consider. So one is the scaling limit and one is a discrete limit. So in the discrete limit, you try to ask what does the planar map look like locally. So you take this random planar graph, this random map. You take a typical vertex and you ask what does its environment, what does its neighborhood look like. So you have some distribution on the neighborhoods. And in this sense, you can try to take a limit and you get an infinite, just an infinite planar map. So the random walk analogy is not so interesting in this case. It just says that you can take a random walk of n steps and you can take a limit and you get a random walk that never stops. The scaling limit is more analogous to the scaling limit of random walks to Brownian motion. So you have this random structure. You can think of it as a metric space with a graph metric, or you can think of the surface with the glued triangles. And you can just rescale this. So you have some random metric space. You can try to rescale it and get some random but rougher metric space. So I'll say a few quick words about the scaling limits, and then I'll talk about the discrete limits. So one of the first results about scaling limit is this one: the diameter scaled by n to the 1/4 and not n to the 1/2 as for random walks converges to some distribution. In fact, it's known what the distribution is, and these guys did much more than just the diameter. Much more recently, there's the works by Legal and Poulan. So they show that the scaling limit actually exists. And again, it was known that in certain other senses, the scaling limit exists before that. But in the stronger sense of random metric spaces, in the Gromov-Hausdorff topology, this was done by Legal. So if you take this Mn, which is this random map of size n, and you take d, which is the graph distance, now you just rescale the distance by n to the 1/4, then this converges asymptotically to some random metric space. So it's known that this space is topologically a sphere, although it has Hausdorff dimension 4. And the conjecture is that this limit is essentially the sphere with a random metric, where the metric is related to the smooth metric by a factor of e to the constant times the Gaussian free field. Yes?
Is this a new result? Because at the end of July it was only non-log subsequences.
What was the?
This conversion.
Yeah, it may be for subsequences. Sorry. Yes?
What's gamma? What is gamma?
I believe it's half in this case.
No, it's square root of 3.
Square root of 3.
X 3. X over 3.
8 over 3.
In some normalization.
So it's a constant. So, a universal constant. Yes, and I should say that. So I should say that, that this conjecture is one of the big missing pieces in making rigorous this approach of computing critical exponents using quantum gravity. So, so far we don't. So we know that the K-P's relation holds within this random metric space in the metric space with this exponent e to the g, but relating this to the limit of the discrete processes is still open. Yes, so this is a map. This is a picture of this e to the g, and I'd just like to point out that this also looks like a planar map, and I may say some more words about this at the end if there's time. But now I'd like to move over to discrete limits. So these were some of the things that are happening with taking the scaling limits of these objects. So how do we take the discrete limits? And again, I apologize to anyone that heard this 50 times already, this definition, but I'll just include. So we consider again a rooted planar graph. So previously the root was an edge, now it's a vertex. This is not particularly important. It can also be a vertex. So we consider just this graph, and in this case it doesn't have to be planar. We just need a root though, which is a marked vertex. And we have this class G star of rooted graphs, and there's a topology on those graphs where two graphs are close to each other if large balls around the root are isomorphic. So we take the ball of radius r around the origin in G1 and the ball around the origin in G2, and we want them to be isomorphic. And if this holds for large r, then the graphs are close. So it's easily metrizable, and those of you in the front rows can see an example here where we have these two graphs. So the up to radius 1 they agree, but once you go to radius 2 they do not agree. So they are not very close. Okay, so this is the topology on graphs, and a couple of quick examples of the limit. So you can take a circle of length n. So when n tends to infinity, this converges to an infinite line. So if you take any neighborhood of any fixed size neighborhood of the root, then it looks like a straight line once n is large enough. You can take an n by n square. If you put the root at the corner, then this converges to a quarter plane, a quarter of the Euclidean lattice. If you put the root away from the boundary, then it converges to the infinite, to the complete Euclidean lattice. One last example, if you take a binary tree and you put the root at what is usually called the root of the binary tree, you take the root up to depth n, then this converges to the infinite binary tree. An exercise for you is what happens if you put the root at the leaves, and I'll just say that you get a different infinite tree. So this is the topology on graphs. Once we have the topology on graphs, we can talk about random graphs. So if we have any distribution on a rooted graph, then we can, any sequence of distributions, we can try to consider a weak limit. Okay, so this holds also without the restriction on the bound degree. But there's an easy fact that if you look at the class of graphs where you have a uniform bound on the degrees, then this is a compact set in this topology, which makes various arguments much simpler. Okay. So this is the idea of this limit, and essentially the way to think of it. So you have this graph, and you ask what does the what does the neighborhood of the root look like? You have some distribution on the neighborhoods, and you can look at this for any finite diameter, any finite radius for the neighborhood, and then you can take a limit, and you get some limiting distribution on neighborhoods for any given radius. Now, in many cases, we want to take limits also of graphs which don't have a root, and in this case, we just take the root uniformly at random. So then, in this case, when we talk about limits of graphs with no marked root, then it just means that we are interested in the distribution of the neighborhoods of typical vertices. Okay, so one theorem that I'm going to prove is the following. So you take Gn, which is a random planar graph, a random planar triangulation specifically, and with a given size. So just a triangulation of the sphere with n vertices. So this is a random rooted graph, and the theorem just says that the limit exists, and in fact it also should say that the limit gives you some infinite planar triangulation. So it gives you some, just an infinite planar triangulation. And there are two parts in the proof of this. So one part, the third part is the easy one, to show that the probability of getting any particular environment converges. So suppose this is the ball of radius r. So you have the root here, and you have some particular ball, and you want to say what's the probability of seeing this particular ball? What's the probability that we have this particular environment for the origin? So we have a ball of radius r. It has some boundary of size m. And we want to say how many ways there are to complete this to a triangulation of the entire sphere with n vertices. So let's say that we have k vertices overall in this ball. So it's just given by the number of triangulations. So once you remove this part, you're left with just a polygon. The rest of the sphere is just a polygon. And you have external bound face of size m. So you now think of this as the external face. And the remainder has n minus k vertices. So you have phi of n minus k and m. So this is the number of ways of completing this to a triangulation of the sphere. And we need to divide this by the total number to get the probability. And if you look at the asymptotics, I'm sorry, there's not 3. So you have an external face of size 3 for the total number. And in any case, if you look at the asymptotics of phi, you can see that the exponential term cancels out. You are left with something that depends only on k and m. And in particular, the limit exists. So this shows that the limit exists. It doesn't show that it gives us a probability measure. So we need some sort of tightness for that. And here there's a very nice argument. And it might remind you of an argument from Ule's talk about considering a random walk on the graph and observing the environment seen from the random walk. And we have the same effect here. So if you take a random walk on the graph, and so if you take a random walk on the graph, so you start at the root and you move, and now you consider the map again rerouted at this point, then you get then this is stationary. So at any given time you get the same distribution. Okay, so now let's look at the maximal degree within a ball of radius r. We want to show that this is tight, and this will give us the tightness that we need.
What is the word tight?
Tight. So it just means that the tail decays to 0 uniformly in the size of the whole triangulation. So we have here a sequence of distributions, one for each n, and we want that the probability that mr is greater than t tends to 0 as t tends to infinity. So this holds for n distribution, but we want this to be uniform in n. Okay, so we want to show that the maximal degree in any finite radius is tight. So for degree 0, just for the degree of the root, this is known, and it's fairly easy. You can compute the distribution of the degree from this sort of argument. Okay, now we proceed by induction. So suppose that for radius r minus 1 it is tight, and now we just observe that the ball of radius r, you can think of it as a union of balls around each of the vertices that are neighbors of the root. So in each of one of those, so if we take one random step, so we replace the root by a random neighbor, and we look at the ball of radius r minus 1 of this new neighbor, of this new root, then this has the same distribution as we started with. So this is the stationarity. And this means that the maximal degree in each of those balls is tight. But we also have quite a small number of these balls. So the number of these balls is not bounded, but it is also tight. So this means that MR is the maximum of a tight number of not independent, but it's a tight number of copies of MR minus 1. And from this, it's easy to see that it is tight. So that's OK. So we finished one proof. That's good. Yeah, I know. So, OK, so one more statement to show you how these things work. So, this limiting result is one-ended, and I'll skip the proof. But one last result. So the size of the ball of radius R grows like R to the 4. This is closely related to the n to the 1/4 diameter size scaling and related to the Hausdorff dimension 4 of the limit. So the number of vertices within distance R grows like R to the 4, even though it is planar and flat. One particularly interesting question about this, and it's a question that in complete generality is still open, is whether it's recurrent or transient. So you have a random graph. That's one of the first questions you ask. Is it recurrent or transient, except when it's obvious? In this case, it's not obvious. So there's the following theorem due to Benjamini and Schramm, motivated by exactly this question. Which is the following. So you take some graphs Gn. So you take any sequence of finite planar graphs, and there's a condition that the degrees are bounded by m. That's the reason for it's not resolved in complete generality. And now you take a root uniformly at random. So you get a distribution on random graphs. You take its limit. Then the theorem is that the limit is a random graph, and the theorem is almost surely recurrent. So if you take a 3 regular map or 4 regular map, so any of a large number of classes of planar maps, then this theorem applies. So it doesn't matter if the GNs are random. So as long as they satisfy the conditions. So as long as you have bounded degrees, you can get that the limit is recurrent. OK, so you might say the 3 regular graph is the dual of a triangulation. And if a graph is recurrent, if the planar graph, then the planar dual is also likely to be recurrent. But there are counterexamples. And again, the conjecture is that this recurrence holds for any class of planar maps that you would care to take. So I'll just finish with a very brief overview of how this is proved. And the idea is to combine this with some of Oded's earlier work on circle packings, which we heard about yesterday. So you take a circle packing. You have a finite graph. So let's assume for a minute it's a triangulation, and this is not really a problem. Then you can consider it circle packing, and you can consider the limit of the circle packings. So it's possible to take this limit, and in the limit you get a random circle packing in the plane, which has the same combinatorial topology. It's a circle packing corresponding to the limit of the graphs Gn. So you might need subsequences here, but that's not a problem. And then you have 2 steps. So one step is to show that the limiting packing has at most one accumulation point, so it's locally finite. And so again. And then the second step is to use a result of and Schramm, saying that if you have a locally finite triangulation with bounded degrees, a locally finite circle packing with bounded degrees, then it corresponds to a recurrent graph. So formally, it uses the notion of extremal length, and I think I'm out of time, so I will not describe this. But I guess I'll stop here. Thank you.
comment on a couple of things implicit in Omer's talk that I find it helpful to try and say explicitly. So the issue is, consider a phrase like random infinite planar graph. Well, that's a somewhat vague phrase. What exactly does it mean? And the sort of, what I find it helpful to say is that there are at least three different things you can mean by that. A couple of which were mentioned here. That is, you can start off by taking some very particular model of uniform on all planar graphs of size n of some particular type, and then take local weak limits, and that gives you these very particular, nice special models. They're special models like Brownian motion or Edish-Renyi or SLE is a special model. The second thing is the sort of Benjamini-Schramm result at the end. You can take sort of arbitrary finite planar graphs and take local weak limits of those. And what you get then is a whole class of processes, which are exactly the graph theory analog of stationary processes. And it's sort of bizarre to me that the Benjamini-Schramm hasn't been pursued much further. It's kind of as if Birkhoff proved the ergodic theorem and then everyone went away and paid no attention to it. You have this sort of fascinating class of stationary processes. You have one theorem about them, but really there are 100 theorems about these things. Start doing interacting particle processes on these graphs instead of on the lattice, for example, and see how they behave. So that's sort of a large class of things. Again, going back to my original saying, what do you mean by the phrase random infinite planar graph? Of course, you can do something entirely different, more probabilistic, and just take a Poisson point process of points on the plane, and then think of some rule for drawing edges in, and that gives you something different still. So, there's all these lines of work, and two of those three ideas Oded was sort of involved with, and somehow people don't kind of say clearly that, there's this vague idea, but it covers sort of lots of mathematically different things. Okay, sorry, I'll shut up.
What was the question?
Isn't that right?
Well, so one general question that you might or might not want to answer. So many people wanted to be students of Oded, but as far as I know, you were the only one who succeeded, or at least half succeeded, because you were also a student of Itai. So what was the secret? How did you?
Private connections.
Can you elaborate?
How did it
Later.
start?
Yeah.
Maybe
You
in
came
the
here as an intern, right?
Well, I was already a student of Oded at the time, so that's why I came here. So, yeah, it started in the Sinai Peninsula, I believe. I think Itai is nodding. So, okay.
Okay, maybe in the reminiscences section you will choose to share some more.
Any more personal questions? So it's my pleasure to announce now the talk by Michael Freedman, who is going to speak about random triangulations as dynamical variables in quantum mechanical models. Michael?
Thank you, Bertrand. I realized I was trying to get Bertrand to give me the last bit of information I needed to give this talk with the mic open in the back room, but I think I got it covered. So the general setting for what I'll be talking about is Chern-Simons theory. And I realize that this is the first approximation, a room full of probabilists. And your experience with Chern-Simons theory may be varied. Now, many of you have brushed up against physics and may have learned it in that way, and some of you were educated in physics. But some of you may not have seen it before, so I want to just put it in context. It's really sort of the child of what's called Chern-Weil theory, Chern-Weil, which is the method of describing twisting of bundles or characteristic classes in terms of curvature. The curvature tensor is a two-form with coefficients in a Lie algebra. And the characteristic classes are polynomials in this two-form, so they're even-degree polynomials. And they give even-degree differential forms. And the Chern-Simons theory is sort of a boundary variation on the theory of characteristic classes where an integration is performed to reduce a dimension. So you sort of subtract 1 by antiderivative to get the Chern-Simons forms. And if you want a typical formula, you'll see something like ADA plus, if it's non-abelian, there may be a term like this, triple wedge of A. And you can think of this, if you have a physics background, as A is a connection in a gauge bundle. It might be electromagnetic gauge bundle, U1, or it might be a U2 gauge bundle, or whatever. Now, Chern and Simons actually had rather modest ambitions when they wrote this down. They were trying to solve some very classical problem about conformal embeddings. This was around 1970. This background is sort of 1940 through 1950s. But it turned out that they stumbled on probably the most well-cited action in the world after kinetic energy. So, it's amazing the payoff to an abstract mathematical investigation. So 15 years after they wrote down the Chern-Simons formula to get a number associated with a particular connection, physicists were integrating over all connections, doing one of these generalized Feynman path integrals. They were looking at things, if this is called the Chern-Simons action of A, then physicists by 1985 were looking at things like the integral over all connections of e to the minus 2 pi I some level k times the Chern-Simons action of the connection. And thinking of this as a perturbed Gaussian integral, you can already see that this is sort of a quadratic form in A, because there are two A's here, with a term which is considered perturbatively. Now, why is this such a great thing to have written down? Well, there are two things about it. One is, it's all written in terms of forms. The metric doesn't enter in. So that means there's no metric in the formula. There's no Gij written anywhere. So this means it's possibly going to give a topological action when written up here. So it's going to give something that might be very abstract and deep and not depend on this geometric structure of space, but just on its topology. That's the first hint that something great has been written here. The second hint is that there's one derivative here. And that's a shock, because in physics, you're used to things in the action which are like 1/2 mv squared. And this v, of course, is a velocity. That's a derivative. When you square it, you see two derivatives in the formula. So you have two derivatives. Now, why is one so much better than two? In condensed matter physics, some of the most interesting stuff happens when you take the noise away at low temperatures. And if you have a translation invariant system, it's always better to think of it in momentum space than position space, because those are symmetries which diagonalize the Hamiltonian. So you always think a k vector at a time. And when you want to see the details underneath all the thermal noise and you go down to very low temperatures, that means you're looking at very small k vectors, very small momentum. And differentiation, as everyone knows from Fourier analysis, in k-space, differentiation goes over to multiplication. So one derivative, if you can see this here, means k, one copy of k, and two derivatives mean k squared, and k will be much smaller. Sorry, k squared will be much smaller than k at low temperatures, low energy limit. So if the system for some reason has a topological term, however weak, it should come to the fore at a few millikelvin. Now, what I'm primarily interested in is topological states of matter. Sometimes call them topological phases. And if you want a very quick definition, it's a state of matter in quantum mechanics, or ground state, which is degenerate. So the ground state isn't one-dimensional, but many-dimensional. And Usually this happens for a boring reason. Like in a magnetic system, there might be a symmetry. Ferromagnet, the spins might point in different directions, and that causes a degeneracy of the ground state. But that degeneracy is easily lifted by adding a small perturbation. But what characterizes a topological phase, it's a ground state that's stable to local perturbation. You can't lift it. So it's a ground state that does not have to do with symmetry and instead is stable. To perturbation. Now, so I don't want to get into this, but we want to build a quantum computer here at Microsoft, and this is how I expect we're going to do it, by manipulating topological states of matter. And Chern-Simons theory turns out to be the main highway to topological phases, our understanding of them. And there's sort of a weaker path that I want to outline today, but the main highway is the field theory approach, which is precisely integrating this action, this Chern-Simons action. And where you land at particular examples of topological phases. You land in these so-called chiral phases, which have like a handedness coming from a magnetic field. They're like right-handed phases. And in particular, you land in a physical world called fractional quantum Hall effect. So don't worry what this is if you don't know, but it's just some very interesting two-dimensional low-temperature system. And many different Lie groups associated to different gauge bundles and different levels K are believed to be seen, or at least glimpsed, in fractional quantum Hall systems. And the degeneracy of the ground state is sort of the computational blackboard or computational space of the computer that we want to build there. But there's another way of looking at Chern-Simons theory, which is more algebraic and starts with the fundamental concept being the representations of the symmetries, the symmetry algebra of Chern-Simons theory. And if you take a representation theoretic approach, then the primary object of interest are the particle types, the point-like excitations of the theory. So I'll just call them particles, which are usually written like A and B. And the first thing you want to know when you discuss a theory of particles is what they might fuse into, which in representation language is which copies of A occur of C occur in A tensor B. So you have these fusion conditions. And then the next most important structure when you start thinking of the algebraic side is the so-called 6J symbol, which tells you how you can reorganize fusion diagrams. It tells you equivalences between processes. So the 6J symbol says that if you see a fusion pattern like this, think of it reading from left to right. So A and C come in and B and D come out, and they maybe have an intermediate particle I. Then a 6J symbol is a tensor which re-expresses this as the summation over A, B, I, C, D, J of diagrams that recouple in the other way. So these coefficients can be calculated from the operator product expansions associated with the CFT associated with the Chern-Simons theory, and you should be able to kind of close this diagram, and you should be able to make other topological phases or models for them by thinking on the quantum algebra side rather than the Feynman integral side. There'll be small differences. We expect to get achiral theories here. So if we're looking for physical models, we probably don't have a magnetic field present. What would the physical model we would try to hit? Well, that's right now a big question mark. We're sort of at the stage of working on the math theory side. We don't really have very strong candidates of what the actual lab system would be, but we're trying to lay a little bit of foundation. Now, you might say, this looks like field theory and this looks like a lattice model. But I want to make the point that that lower path is not quite a lattice model. Because if you notice, not only did the letters change a little bit, which are sort of the states on the lattice edges, on the bonds, but actually the diagram changed, the lattice changed shape. You know, the left diagram and the right diagram are like a little piece, but of different lattices. So if you want to build a Hilbert space, the natural kets, or basis vectors for the Hilbert space, will be a pair, a lattice, or I'm calling it a triangulation, and a labeling of it. So a triangulation and a state. So the triangulation, I don't know, it sort of should be implicitly visible in these pictures as the dual structure. I sort of drew the dual thing, but in red I could also draw the triangulation. And you see, if you're used to these pictures, that I've done kind of a famous thing to the triangulation on the left to turn into the one on the right. I did this plaquette flip, where I took this vertical bond and I turned it horizontal. So that means we don't have really a fixed lattice, which is traditional in condensed matter physics. That's what most of the literature is. But we have a fluctuating lattice. We want to work in a Hilbert space that contains both sort of quantum gravity and labeling. So it relates to the previous talk. And what the Hamiltonian will look like, just whimsically call it quantum gravity Hamiltonian, is we'll have some terms which are the topological enforcers that will enforce the fusion rules that I explained, A and B fused to C, and will enforce the 6J symbols. We'll have a term which allows defects, so I'll call that delta capital D. Well, it actually penalizes defects by an amount delta. And perhaps some other terms in perturbation, which I'll come to later. So the point is, if we had a fixed lattice structure, like a honeycomb, I know mathematicians don't call this a lattice. I mean, it's not a, it's two lattices. But, physicists do. Okay, so yes.
Are you interested in having a lot of quasi-particles in this fluid? Or why are you talking about lattices? It's just finite graph, very small typically, right?
No, I'm thinking of...
two quasi-particles, you use them, that's it, right?
No, the underlying topological fluid will be made of this sort of string network of particle lines, but they're not the quasi-particles of the system. So there are two levels, and you're confusing the two, and I understand why. So the mathematical input to create a topological phase is the fusion algebra for the representations of some quantum group. Now, on the one hand, you could think of those letters, A, B, and C, as the excitations of some system, and you're asking me about those. But I'm not using them as excitations. I'm trying to build the ground state of what's called the quantum double by inputting the fusion relations from the original algebra. So you could look at a picture like this and think that it represents a one plus one-dimensional physics of some particles moving from left to right. But that's a way of thinking, and it's a good way of thinking, but it's not literally what I'm describing. I'm describing 2 plus 1 dimensional physics, and the 2-dimensional ground state will be encoded by some large lattice or fluctuating lattice of bonds encoded by, labeled, decorated by particle types from some representation theory. I don't know if that helped. But I am thinking of a large lattice. And I'm thinking in particular the lattice might just be the honeycomb, but it'll have to, for this type of model to function, there'll have to be provision that allows defects to be formed and removed. It'll have to be possible to flip bonds, to like heat up the honeycomb and let it fluctuate in order for the 6J symbols to function. How am I doing for time? So now where does Oded enter? I realized this lattice would be fluctuating, and I thought that might be a problem. So I emailed Oded and told him that I had heard that there might be some slow or moderate relaxation times associated to the space of triangulations. So specifically what I asked him about was, suppose you take the two-sphere and you take triangulations on it, and just to make it concrete, you fix the number of triangles as n. And you think of this as the vertices as of the graph, and the edges of the graph you think of as these flip moves that I highlighted before, the plaquette flip. And now this is a graph, and you look at its incidence matrix, maybe minus the incidence matrix. And what I wanted to know was the spectral gap of this matrix. And so I'd call this lambda, this gap. It's related to the lambda of yesterday by a very simple formula. Well, it turns out that this is algebraic in n. It's probably something like n to the minus 1 with my normalization, where I just take this as the incidence matrix. I'm not taking the probabilist normalization yet. But Oded said we could learn a lot about what was going on if we just concentrated on the outer planar case, because everything there was given by Catalan numbers, and we could work everything out and we'd understand, and then we'd at least know sort of roughly what we were talking about. So over email, Oded gave me this lovely lecture in combinatorics. So we replaced this with the outer case, where we look at a fixed polygon, and we consider only triangulations where we add no new vertices inside. And as you all know, these are counted by 1, 2, 5, 14, and so on. These are the Catalan numbers. Cat n, which is, I'm sure everyone in the audience can correct me if I make a mistake here. It's roughly equal to an exponential, which again is not the important part, and then a polynomial piece, which is n to the minus 3/2. So since I was asking a spectral question, and Oded thinks very geometrically, he said we should think about this in terms of the Cheeger point of view. We should look for, like, where's a narrow place to cut the space of all triangulations, outer planar triangulations. We want to think of this space as roughly looking like, we want to sort of know if it's long and thin and see if we can find a way to cut it into two pieces to see how it would vibrate and figure out what that lambda is. So that's the art. You have to have some inspiration to figure out how to cut these infinite dimensional graphs, And he told me to cut it into the thick part and the thin part. And I asked him what that was, and he said, he said every outer planar triangulation, so I won't draw all the vertices around here, has what's called a central triangle, and it's unique. Well, there's a detail. Say there's an odd number of vertices on the boundary, then it's unique. So I don't know if this is a standard notion, but what the central triangle is, it's the one triangle in the picture where the fraction of vertices on the three sides is all less than 50%. So you have n1, n2, n3 vertices here, and each of these ni is less than or equal to n over 2. Okay? And it's quite clear that there can't be more than one of these, because if you have one and you go to the side, then one of these edges from something on the side will involve the sum of two of the previous terms, and they'll be much too big. So uniqueness is easy.
What class of triangulations are you looking at?
Outer planar.
Outer planar.
That means there's only the vertices on the edge of the polygon. You don't.
There's a tree structure.
It's equivalent to a dual. There's a dual tree structure, and those are counted by Catalan numbers. So there's. But then Oded said a lovely thing, which is very much what he would say. He said, well, now, of course, you know why there is a central triangle. It's the fixed point theorem in the disk. So the point is, you imagine each of these triangles to be endowed with a sort of a vector field where it flows in on the long side and flows out on the short sides. And if there was no central triangle, you'd retract the disk to the circle. So that's how you show there's a central triangle. Now, the definition of thick and thin is you just take the smallest ends, call it N3. Say N1 is greater than or equal to N2 is greater than or equal to N3. And you just say N3 is greater than or equal to N over 10, or N3 is less than N over 10. 10 is more or less flexible here. And this is called thick, and this is called thin. And it basically cuts the graph, the hypergraph, or the high-dimensional graph of outer planar triangulations into two classes. And now you can just kind of count away to your heart's content. You only need Stirling's formula and this approximation to the Catalan number. And you can figure out that roughly you have order 1 thick ones, order 1 thin ones. You can figure out how many are near the boundary, and you can figure out exactly what the Cheeger constant is. And the conclusion is that you get an upper bound. You get n to the minus 1/2 is greater than or equal to this Cheeger isoparametric constant k, which of course then gives a bound on this lambda I was asking. And this translates immediately to the mixing time being greater than or equal to n to the 3/2. It's sort of the reciprocal of this exponent, but you get an extra 1 there because for talking mixing time, you should go to the probabilist normalization of the incidence matrix. By the way, there's an important difference there if you do some physics as well as probability you should be aware of. In probability, it's very natural that if you have d guys you're going to, then the probability is like 1 over d, you'll move to any one of them. But if you're thinking physics and you have d interactions with other people, just because you're interacting with a lot of people doesn't that weaken those interactions. There's no reason to divide them by anything. You know, you have a lot of assassins stabbing you with knives, they'll all hit you with the same strength.
Some of us think of other interactions.
No, actually, from computer simulations, I think this is.
Typical physicist interaction.
Yeah, not the math world, right?
So the probability of looking at the shoes of one of your neighbors gets sort of smaller and smaller.
So, by the way, so all these numericists, I don't think I mentioned them at the beginning, I wrote them on the board. So this is, what I'm discussing is all joint work with 4 numerical physicists who've been trying to see if anything I'm saying makes sense. Matthias Streuer, Simon Treps, Charlotte Gills, and Sergei Isakov. And they've done numerics on all these topological issues that I'm now getting to.
What was their verdict?
I think they're still out. I won't speak for them. So by the way, I think even in the outer planar case, this beautiful idea of Oded's maybe didn't hit the, I'm not sure if it actually hit the best cut, found some cut, because the simulation seems to give us slightly slower mixing. I mean, now, why was I worried about this probabilistic sounding thing of mixing time? If you want to construct a topological phase, you really need a gap above the ground state to protect the information. And I was worried that any model that had quantum gravity aspect to it would be gapless. And the gaplessness would damage the robustness of the topological information. And in fact, these models are slightly gapless. And this isn't a very
Slightly gapless?
well. I mean, you could have a much worse situation. You could have the gap decaying exponentially in some parameter. I mean, it's a low polynomial.
Yeah.
I mean, it's not. It doesn't meet.
In n.
Yeah, I mean, right. I mean, it's not good. It's not. It's still not good.
It's not good.
It's not good.
Call it gapless.
Yeah, it is gapless. It just.
Okay.
It just different communities don't call those powers gapless, but I think of them as gapless. Yes.
You were originally thinking about general triangulation, right? So is there any reason why you would expect the outer case to be the same as the depth?
Oded was just sort of warming us up with this. Yeah, that was his guess, that they had the same exponent. And the numerics actually we did on we did them on both, and they were the same. Okay, so the last part of this talk is to try to explain.
Mike?
Yeah.
So one thing, I mean, the Chigger bound doesn't give you a sharp bound.
Yeah, I know. There's a square that could come in. Yeah, I know. I know.
Prasad, did you have something?
So, yeah, I guess I might have distracted Oded with the outer planar because that was the case I knew about. And Dr. David Aldous had posted.
Yeah, I mean, it isn't my result, but this has been known for 15 years. It was actually this n to the 2/3 argument. I forget who it was from, who first thought of this.
The n to 3 half, but it's interesting if the simulation suggests n squared over here. Because it's still open.
Right, it's still open.
I see.
Been on my list of open problems.
Okay. Yeah, actually, I did know I did find out about your work, and I should have mentioned it.
Well, good, no.
But my usual practice was just to ask Oded first before wasting time typing anything to Google or Wikipedia or Bing. Okay, so the question is, what can be done about this gaplessness? Can you make a topologically protected model off lattice? And basically, there are two answers, two ways to proceed that both work. And one is called, I think of as the timid approach, and one is the bold approach. So the timid approach, in the Hamiltonian that I wrote down, is just to make defects very rare by setting delta toward infinity. You make delta a very large constant, you really penalize defects, then basically you're only working on the honeycomb with tiny quantum fluctuations around it, so that it would cost a lot of energy to change the honeycomb, and you only get virtual processes that drag you out of the honeycomb into other lattices. Now when you do this, you actually can prove that you get all the topological phases you expect, assuming you trust the perturbation theory, which I think can be made rigorous in this case. But you get a spectral gap for the topological phase on the order of 1/4 raised to the 55th power times the bare energies of the terms. Now, this is a very small gap and probably not useful for building a computer. Now, why is the gap so small? It's because in this picture, the quantum fluctuations around the hexagon tiling that are important are the ones that would eventually do something topological, rotate this plaquette B all the way around A. And you can ask how many F moves, how many 6J moves are required to do that. Now the first one would be just to rotate this spoke to there. This spoke to there would be a second one. This spoke to there. Now we've done 3. You do 3 more and you've moved you do a total of 9, and you've just moved B to B prime. And then you have to do that 6 times to get it back to where it is. So you get 9 times 6 equals 54. So you get 54 F moves. And you have to, then there's a creation and annihilation step, so it turns into 56, and then you get a 55 in the denominator. So this is only intended for those who are familiar with perturbation theory and know about energy denominators and so on. But so timidity gets its usual reward. Okay, the bolder approach is to set delta all the way to 0 and sort of face the quantum gravity head on. So now you're not in the crystalline phase where you're working around and now what happens is in this phase, you made the cost of a defect so expensive that the kinetic energy benefits associated with proliferated defects were balanced and the defects were confined or didn't even happen. Here, kinetic energy takes over and the whole thing becomes just a sea of defects, and you're in a quantum liquid. And in fact, the measure should be basically one of the measures that was discussed in the last talk. You're sort of randomly sampling a random triangulation. And you will have to then think about these gapless gravity waves, which we call them. So the result is a very novel phase which succeeds in protecting some topological information, but on the other hand has gapless gravity waves. So normally you'd expect this to be very risky, but the point is there's a gap to topological excitations, even though that there are another class of excitations which have low energy. So they seem to sort of pass in the night. I mean, it's not physically implausible. I mean, for instance, you could have the disjoint union of two systems. One is topological, and one is just a vibrating string, and one's gapless and the other isn't. So it's something akin to that that's happening here. Thank you.
I have a rather ill-informed question. Why decompose the structure of that Hilbert space that way? Why defects? Why not embrace more of the topology of the first term, I guess is another way to say it.
Well, the point is that the topology of the first term involves these two ingredients,
right.
The 6J symbol and the fusion rules.
Right.
And the 6J symbol can't operate unless there's a defect. That's the point. If you start with, imagine this gets completed. I won't draw it all out, but imagine you start with this picture and you draw the honeycomb, and then you insist that this happens.
Yeah.
What that does is it turns this into a 7-gon and this into a 7-gon,
Yep.
and turns this into a 5-gon and this into a 5-gon, and the rest are all 6s out here. So this is what I'm calling a defect.
I understand.
Well, so the point is the way of inputting the topology was by the form of the 6J symbol. The 6J symbol has no scope for action unless there's some defect, at least virtually.
Yeah, I guess I'm questioning whether the neighborhood is all 6-gons, is another way to say it.
Oh, it will be.
Well, but is there some topological framework in which the 6J rule can apply, but it's not a defect in a sea of hexagons, it's rather just a sea of that stuff where things flip and migrate, but it's but it's more regular. It's not noisy or chaotic. It's actually more topological.
Well, you see, this is actually goes right to the heart of quantum gravity studies, and what I was trying to learn over the open mic just before the talk is people have hoped to describe ultimately the physical universe by probability measures on triangulations. And what they were hoping for is to get something that wasn't boring, wasn't just a fixed crystal with maybe exponentially small fluctuations around it that would allow there to be galaxies and whatever, some variation on the background. So it should be somewhat flexible, but it shouldn't have Hausdorff dimension, twice what's expected. It should be approximately flat space, in this case 2 space or 4 space for real physics. But they sort of searched in vain for 20 years. Trying to find a reasonable homogeneous Hamiltonian that would give a phase that was halfway in between a crystal and a wild sea of everything. So that's sort of the big failure of quantum gravity. Now there's something called causal dynamical triangulation, which has been big on the quantum gravity scene in the last 10 years, where they break the symmetry. They break symmetry. They have 3 directions picked out as space and 1 direction as time, and they give weight to the edges of the simplices differently depending on whether they're space-like or time-like. And with that structure, they actually can succeed in enforcing flatness in the correct dimension. Problem with adapting that to condensed matter is that causal structure, which is so useful in allowing fluctuation but enforcing global flatness, doesn't allow braiding. You can't braid excitations around each other when you enforce this causality. So we looked at it and enjoyed it, but we didn't try to incorporate it since we're at work on a serious project.
Sort of applied,
I think we have to finish at this point.
Okay.
Thank you again.
Thank you.